Okay. We are ready to rock and roll. We did permutations on Tuesday, right? Where we talked about how can we arrange a set of letters A, B, C, okay? And we know how to make 2-letter word sequences. And maybe what I should do is, if we have A, B, C, and we want to make a 2-letter word sequence, then I recommend using the slots, right? And we list how many options we have for each slot. Now, the first slot I have out of A, B, C, I have 3 letters to choose from. Okay? But then if I am not allowed to repeat any letters, which is kind of implied here, then I have 2 options for the next letter, which gives me 6 different combinations or permutations, I should say. And so what that means is that we get AB, BA, BC, CB, AC, and CA. This is what we call permutations, right? That's permutations from last day. Now, what if we don't have letters? Maybe we have Al, Bob, and Chris. And we think about a committee. Committees of 2 people. Whoops, I need my pointer. 2 people. Then it doesn't matter if we have Al and Bob. That's not a different committee from Bob and Al, right? That's the same committee, right? Someone would say, you're bonkers for counting those committees twice, right? And so really, we can summarize the committees as AB, which also involves BA, BC, which also involves CB, and AC, which also involves CA. Okay? And so these are what we're going to call combinations. Okay? And so here we can call these combinations. The key thing to think about is that the order is not important in these combinations, right? Al Bob is the same as Bob Al, okay? And so we have 3 committees and not 6. Okay? I'll highlight this last piece here because that's really the one that I stole it all for. Permutations are arrangements where the order is important, right? In terms of a word or kind of letter combinations, AB is different from BA, right? And so then it does matter which order things happen in. Okay, so the permutations are arrangements where order is important, right? Think about AB versus BA, right? Different word. While combinations are arrangements where order is not significant. Right? And so if we think about Al and Bob is the same as Bob and Al. I should say Al and Bob is the same as Bob and Al. So then order doesn't matter. You just have a group of people. This is generally not the easiest thing to land on right away, right? But it is a good guideline for kind of figuring out, okay, is this a permutation or is it a combination? So let's give it a shot. Given the set of letters A, B, C, D, we want to write the number of combinations of 3 letters. And then from these combinations, determine the number of permutations. Just so I Don't muck it up. You can try it, right? ABC, oops. Okay, fine, I'll do it. ABC, then I'm gonna change one, ABD. BCD. And I don't think I have an ACD. It's easier if you do them kind of in alphabetical order, because the order doesn't matter, right? And so this group, BCD, is the same as DCB, is the same as DBC, it's the same as CBD, right? All of those would be lumped into this grouping, right? Or this combination. And so here, these are our combinations. So we have 4 combinations of 3 letters. And then from these combinations, then we can determine the number of permutations, right? Then we can focus on ABC. Well, we can morph ABC and move things around, but oh, they looped around, didn't they? Ah, dang it. Can I change something to match these? Otherwise, we're gonna have to think of all these 24 things by hand, and that's hard. So I'm gonna change this. ABC is good, but then they have BCD, CDA, and BDA just to match. Otherwise, I'll be hooped. BCD is this one here. CDA is this one here, and BDA is this one here. So we had them all just in a different order. And if I wasn't trying to steal the solutions from the textbook, that would be fine. You can just go ahead and do it. So now we're going to list the permutations, right? How many permutations of A, B, C? So of these 3 things, do I have fitting into 3 slots? Right? I'm going to have this first one, and then 3 times 2 times 1, right? For the number of permutations, right? And so here, I have 3 times 2 times 1 permutations. But the first one that we listed is one of them, which means I have 6 permutations. So stealing them from here, I have ACB, BAC, BCA, CAB, CBA. Remember, we did this one as a tree, right? To figure out all the 3-letter permutations of ABC, right? Depending on which branch you went down first, right? That would determine the remaining letters. Okay? And now, I'm just gonna jot down BCD, BDC, helps if I do it right, CDB, CBD, DCB, and DBC. CAD, DAC, DCA, ACD, ADC. Can you imagine if we had to do these by trying to figure out, well, you could do each of them with a tree diagram. Right. Set up your 3 letters, build them all out, list all the different permutations, but that's not what today is for. It's just for these guys, the combinations where the order doesn't matter. So this, we established that 3 factorial is how we could summarize that. 3 factorial is 3 times 2 times 1, and so there are 3 factorial combinations, permutations. My apologies. Which means that there are 4 times 6 different permutations. Therefore, there are 4 times 6, which is 24, but let me confirm. Phew. Permutations of 4 letters into length 3. So how do we get from that 24 down to just the 4 combinations? Right here, we said we have 4 combinations. I should have put that there. Well, you could say that, let's start with 4p3. So 4p3 is 24, right? 4 letters into length, into 3 slots is really what it's saying. Right? How many ways can I do that? I can do that 24 ways. Each of these groupings, right, could be split into 6, right? 6 here, or 3 factorial, which is linking it back to this 3 here, this number of slots, right? And so that length 3, well, each of those have 3 factorial, right, that are kind of redundant. We only need one of those things. So notice, and you don't need, I'll give you the formulas. Oh, that's what I was, wow, I just jumped right into it, didn't I? Combinations. No complaints. Only on Zoom on Tuesday. Okay, just a reminder. And I was working on a practice test, but then I had to go to that meeting and I blame it all on them. But I'll post it when I'm finished, which will be by the end of the day tomorrow. Today's like done. I'm tired. But I'll post it. And then what I want to do is I want you to try it before class on Tuesday. And as a bonus assignment, I'll let you submit your work for another completion mark. And then we'll go through it together on Zoom on Tuesday. But I'll also post the video as always. Okay? And so that's my plan. And it was all hinging on having this practice test made to give you paper copies. I know, so rich. But I didn't do it. I didn't finish it. So close. Yeah. Tuesday is on Zoom only. So no class. On Zoom. Yeah, but not here. Yeah, I won't be here. That's all. Yeah. But during the class time, and then if you can't make it for whatever reason, then just watch the video after. Because we'll work through the practice test together. Yeah, yeah, exactly. Okay, that's what I wanted to say. More of a confession, I guess. What was I going to notice? Notice, the number of combinations is 4p3 divided by 3 factorial. We said 4p3 is 24 and 3 factorial is 6. 24 divided by 6 gets us to 4 combinations. So like I said, that's kind of lofty, but in general, what we can say in general, we're going to develop this NCR instead of NPR. Now we have combinations instead of permutations. And the NCR, which is a button on your calculator as well, is technically taking the NPR divided by R factorial. Or from there, if we remember the factorial definition of NPR, it was n factorial divided by n minus R factorial divided by R factorial. Don't worry, you'll just have the final result, but I do want you to see it. This is a fraction over a fraction, right? R factorial is just R factorial technically over 1, right? So if you flip that and multiply it, you get this. NCR is n factorial over n minus R factorial times 1 over R factorial. And that's how we get the factorial definition of NCR, which is just n factorial over n minus R factorial, R factorial. Good. So this is how many ways can I rearrange n objects into R slots, but now order doesn't matter. And so that's what the combinations are going to tell us. It was acting up again, so I have to do this weird. Probably don't have to. Have to be less old to handle it. So a combination is a set of elements. Oh, of a set of elements. Like, is a set of elements is an arrangement? No. Of a set of elements is an arrangement where each element is used once and the order is not important. That's probably the take-home message here, right? Thinking about committees, right? Flipping a coin, if the order doesn't matter, you just want to know, okay, how many ways can I flip 4 heads in 10 tosses, right? Then it doesn't matter when those 4 heads happened, right? But they had to happen at some point, right? And then we've got this formula that we just developed. Let's work with this little guy. Has some formatting issues. Okay, fine. There's another excuse that I have for not finishing your practice. I was really kicking butt on, can I say that? I already said it, with my formatting. So in math, we do all our typesetting in LaTeX. It's a typesetting language. It's like a programming language. This author is not very good at it because that's bad. But whenever you see stuff like that, then, but I was, yeah, doing some pretty cool stuff. You'll see. Okay. You might not even notice. There's that slight possibility. All right. If we have to compute these things, now I encourage you to check your work with your calculator, but I do want you to be able to do it using the factorials. And so you can check your work with your calculator, but you need to show what you did. So 5. I read as choose 3. How many ways can I choose 3 things out of 5? Okay. And so technically it's, you know, out of 5 combined into 3, right? But I think it's nicer to read it as choose. And sometimes we call it the choose function. So n factorial, n is 5 in this case. And so I have 5 factorial divided by 5 minus r is 3 in this case factorial times 3 factorial again. Now, how I approach these to simplify these is I simplify the 5 minus 3. So I have 5 factorial divided by 2 factorial times 3 factorial. And then the trick is to write out 5 factorial until you hit the biggest of the factorials in the denominator, because then you can cancel them. Okay. Comme ça. 5 times 4 times 3 factorial. All right, that's my biggest factorial. And then I'm left with 2 factorial, 3 factorial. This, I went to 3 factorial because it cancels. You could go to 2 factorial, but 3 factorial is bigger. And so if you can lob that off, right, that's gonna make your calculations a little bit easier. Because what's 2 factorial? 2 times 1, just itty bitty. Hardly even counts. And so here, write 5 factorial until the largest factorial in the denominator. And then cancel. We're allowed to cancel because we're multiplying. Score. Now, all of a sudden, this is relatively simple, right? 5 times 4 divided by 2 times 1, just as a reminder. 5 times 4 is 20 divided by 2, puts me at 10.
Do you want to see this one?
Yes.
Okay. Will you say like?
This section is a bonus question.
Okay.
But yes, I do want to see this math. But I will give you this formula.
The whole thing?
This, yeah.
Okay.
So not too bad. Not too bad. And then you can confirm it with your calculator, right? Confirm with your calculator. Now, depending on your calculator, right? I would say almost, no, any scientific calculator that you have is going to have an NPR button and an NCR button. Just a matter of finding where it is. And then your individual calculator, maybe get to know how it works. I have to do my 5 and then hit the NCR and then 3 and then equals, but I do get 10. So make sure that you're able to get that. Some calculators have a C and then N comma R. So it just depends on how your calculator works. I'll remove that because I think that's pretty rare, but you can confirm it with your calculator, which is always nice. Right? Be able to check your work. How luxurious. 7, choose 3. Let's see. Can do the same thing again. 7, choose 3 is 7 factorial. Divided by 7 minus 3 factorial times 3 factorial. Got buggy. So now 7 minus 3 is going to be the bigger factorial. So I'm going to write this out. 7 factorial divided by 4 factorial times 3 factorial. You can skip this step if you want and go straight to this step. 7 times 6 times 5 times 4 factorial. Right, go until the biggest thing in the denominator, and then you're able to cancel them. There's nothing wrong with writing them all out, right? But it gets really messy and really big. So now 4 factorial can cancel. And then I'm just left with 7 times 6 times 5 in the numerator, which is a little bit more reasonable, which is what? 7 times 6 times 5 is 210. Divided by 3 factorial, which is 3 times 2 times 1, which is 6. I get 35. We can confirm with our calculator. 7, choose 3, 35. Maybe you guys can read this question and get it right away. I had to think about it because I'm like, well, that doesn't make sense. But the scenario, after I thought about it, should be this. In how many different ways can a student select to answer 5 questions from a test that has 7 questions if the order of the selection is not important, right? And so now I give you a test with 7 questions and I say, you have to do 5 of these, okay? Then if you did them in order, right, 1, 2, 3, 4, 5, let's say, that's going to ultimately look the same to me as if you answered them 3, 2, 1, 4, 5, right, etc. So it becomes this kind of a group of test questions that you've selected. And so that's what makes it a combinations problem. But initially, I think maybe it was just reading too fast. And I read it as a multiple choice question, right? But it's not. Because if you have 7 multiple choice questions, right, then we talked about how many ways can I permute those answers, right? But here, the scenario is you have question number 1, 2, 3, 4, 5, 6, 7, and you pick 5 to submit. right? For example, 1, 2, 3, 4, 5, because I'm not very creative, would be considered the same as 3, 2, 4, 5, 1. 1, 2, 3, 4, 5, yeah. And so that's why we're talking combinations here. So out of 7 things, I have to choose 5. Right. Out of 7 things, choose 5. I'll clean up this choose. Seven factorial over 7 minus 5 factorial, 5 factorial. You can skip some work here. 7 times 6 times 5 factorial divided by 2 factorial, 5 factorial, like that. 7 times 6 divided by 2 times 1 is 7 times 6 divided by 2 is 21. I've actually done a test like that where I gave, 5 different questions and my students had to pick 3 for me to mark. You're allowed to try them all, of course, but you had to tell me which ones to mark. Tricky. Decisions. Everyone wanted bonus marks for doing all of them. No. Okay. How many line segments can be drawn by connecting any 2 of the 6 points that lie on the circumference of a circle? Well, let's map it out. I can draw a circle, and maybe I have a point here, and a point here, and a point here, and a point. I guess I shouldn't have done it like that because that makes 4 points and I need 6 points. Let's just spice things up like this. I could have done them spaced out better, but it's over. If you label these points, right? A, B, C, D, E, F. You could turn this into a problem that you've already been working on, right? By saying, okay, well, what's a line segment? A line segment is going to be anything that connects 2 dots, right? Could be A to F, but A to F is the same as F to A, right? And A to C is the same as C to A, right? And so instead of drawing all these out, right, we could even go B to C, right? Line segments are just combinations of 2 letters, right? And so here, notice line segments are just combinations of 2 letters. since A to C is the same as C to A, same line segment. Part of this problem solving is trying to morph the problem that you have into a problem that you've already seen, right? That you already know how to solve. So now, if we have these 6 points, right? A, B, C, D, E, and F, right? How many combinations of length 2? Do we have? 1, 2, 3. Yep. That sounds like 6 choose 2. Six factorial divided by 6 minus 2 factorial times 2 factorial is 6 times 5 times 4 factorial divided by 4 factorial 2 factorial. That 4 factorial cancels. 6 times 5 divided by 2 times 1. Makes 15. Which I confirmed. Just in case. So there are 15 line segments, and I mean, as kind of a fun exercise, you could see if you could draw them all, knowing how many there are. Right? There are 10 people at a party. If they all shake hands, how many handshakes are possible? Hello, hello, hello. Right? Al shakes hands with Bob, but that means Bob shakes hands with Al, and it doesn't really matter. It's the same handshake, right? So if Al shakes hands with Bob, that is the same handshake as Bob with Al. 2 birds, 1 stone, if you will. And that tells me it's a combination. So I look at how many do I have? I have 10 people at a party, and a handshake traditionally is 2 people. So let's stick to that. That's feeling a little culty. Welcome to the party. That's why I said traditionally. Traditionally, yeah. Traditionally, just 2 people. Divided by 10 minus 2 factorial, 2 factorial. 10 times 9 times 8 factorial. Once you get used to the kind of stopping at whatever the biggest factorial in the denominator is, right? Then it simplifies things a lot, right? I wouldn't mark you wrong. I'll do it here. You could say, maybe I should use I don't know, different color. Or if you wanted to, you could say 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Phew. Divided by 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 2 factorial, which is 2 times 1. That's not wrong. I wouldn't mark you wrong for that. It's just a ton of work, right? That you don't really need to do. Right? Then what could you do? In that case, if you were tempted to simplify, you'd probably end up doing that. And then you can simplify an 8, you can simplify a 7, a 6, a 5, a 4, and a 3. And you'd be left with the exact same thing, right? 10 times 9 divided by 2 times 1. So it's just a little bit, I think, a little bit quicker to do it just writing to the factorial, but you're welcome to do it the other way. Right? Because from here, these guys just cancel. And I have 10 times 9, which is 90 divided by 2. So I get, I should write it up, divided by 2. Oh, 900 divided by 2 is 450. I don't know where I got, I think I did an extra 0. Everywhere. Let me confirm. 10 times 9. Yes. Divided by 2. Yes. Good.
There's a lot of plus ones.
Yeah. Or just tack on a 0. An extra 0 never hurt, right?
It's a big party.
Yeah. Mm-hmm. 45 handshakes. Could get it done pretty quickly, I think. Hey, how are ya? Hey, how are ya? And now you know if you're at a party and you want to shake hands with anyone or everyone.
Shook hands, 45 handshakes.
I
Just
know.
walking to parties and helping them.
Did you know? I mean, you could try it. Let me know how it goes.
Next party check. Hey. Fun fact for you.
You could even count how many are there. Do some quick math, right? Cancel those factorials. Really show off. I'd be so proud. Ooh. How about this one?
I skipped this one. I did the other one.
That's fair.
Well, I don't know if I did it right.
The shopping area of a town is in the shape of a square that's 5 blocks by 5 blocks. How many different routes can a taxi driver take to go from one corner of the shopping area to the opposite? And when I read this, I was like, cater corner? I've said kitty corner like all my life. Cater corners? Kitty corner. I always called it kitty corners. Do you guys, what do you guys call it?
What is a kitty corner?
It's like this.
A round corner. Like
So
you
here.
be going all the way up. That's good.
So it's gonna look like the, I guess it's a square block. 1, 2, 3, 4, haha, 5. So it would be from, for example, down here to up here.
Gotcha.
That's the cater corner, but my world shattered. I thought it was kitty corner, which is so cute.
Mm.
Whether it's a child or a cat, I'm not sure. Because clearly it's neither. Yeah. Lots of room for misunderstandings. So the first thing we want to do is we want to map this out. Right. And so it's 5 blocks by 5 blocks. So we've got roads running like this. 1, 2, 3, 4, 5. And then I'm gonna try to recreate the magic here. 1, 2, 3, 4. Just might have pulled it off. So how about we approach it the other way? How, we're in the combination section. That's kind of telling, right? That it's going to be a combinations problem. But how can we make it a combinations problem? Let's see here. What are some possible routes? Well, to get from A to B, let's say, I could go, how can I'll highlight it. I could go straight up and over. Or I could go straight up, 1 over, then up and over. Or I could go up and I could go over. I could go up 1, I could go over 1, I could go up 1, then over. So many options. Let's see here. Either way, how many blocks are you traveling? 10, right?
10 is what I said. Yes.
Yeah, I couldn't quite hear you. I actually couldn't, so. But the way you said that. Right? 1, let's look at our simplest route. 1, 2, 3, 4, 5, and then I have to go over 5. Right? So I have to travel a total of 10 blocks. Yeah. Same thing with the next one, right? I go up 4 and then I went over 1, so that's 5, and then up 1, so that's 6. And then I have to travel another 4. So that's a total of 10 blocks still. Huh. Okay. Now, let's see here. I am cheating. That's right. What if we label these blocks, anything traveling up, you can label them up, north,
Yes.
or vertical. Doesn't matter. Right. As long as you put a label and you say, okay, all of these moves are up or north or vertical, right? And then all the sideways moves are going to be over. Up and over is kind of the terminology that I was using. Over, I guess, would this be east? Or horizontal? Makes sense too. If we think about all these routes, or those few routes that we took, and we count how many vertical blocks we traveled and how many horizontal blocks we traveled, right? We started off and we did 5 horizontal, followed by 5 vertical. Right, up and over. Then we did 4 horizontal, 1 vertical, 1 horizontal, 4 vertical. Right, that was this, I don't have a way to differentiate them. 4, they're just all highlighted in a hot mess. 1, 1, 4.
No matter what, it's like it's 5 vertical, 5 horizontal.
Ding, 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 ding. Yes,
Wow.
exactly.
I said it. Yeah.
So we'll always need to move 5 vertical and 5 horizontal. So what you can do, and this is where it gets a little bit wild, so just accept it. You only need to choose one of those two, right? So out of those 10 blocks, right, you pick 5 to be your horizontal blocks, right? And then the remainder will just kind of be determined by what those 5 horizontal blocks are. Okay? And so, for example, if it picks just randomly, let's say it picks, I don't know, this one and this one and this one and this one. What's that? 1, 2, 3, 4, 5. Seems weird.
I don't know.
I don't know.
You can only go
1,
up,
2,
because
3,
you have to
4.
switch the
Yeah, how can I get over there? Yeah, okay, so it has to be,
The third and the fourth one, you can switch.
My brain.
how about there?
Ah.
That actually works.
So they do have to ladder up. Fair
You
enough.
don't get to go backwards.
No.
They're one-way streets.
Then 1, oh, I should use a different color.
But I don't think that actually works. One-way streets?
1,
It's true.
1, 2, 3, 4, 5. Nice. So if you're prepared to just accept it as truth, well,
Emily's gospel.
so this is being recorded, so I like what I'm hearing, although I'm pretty sure they can't hear it.
It's on the record.
It's on the record. Yeah, I'll play it before I go to sleep.
Yeah,
Oh, yeah.
repeat. Make the loop. Then you can make it a rap.
Or vertical. And the remaining 5 will follow. So out of 10 blocks, how many ways can I combine 5 of those or choose 5? 10 choose 5. It's 10 factorial over 10 minus 5 factorial times 5 factorial. 10 times 9 times 8 times 7 times 6 times 5 factorial. That's a long one. Divided by 5 factorial, 5 factorial. divided by 5 times 4 times 3 times 2 times 1. All right. Times 7 times 6. I'll jot it down. Just in case I did it weird. 9876, yeah. 30240. Divided by 120. 252 roots. This taxi driver could take almost a new route every day. If you exclude holidays and things like that, right? Lucky driver. It's exciting. It's the last one,
It's a good one, it's not very long.
right?
We did it.
We did it. Perhaps, unless I really drag my feet. If a coin is tossed 6 times, in how many ways can it fall 4 heads and 2 tails? So now it doesn't matter which order they appear. It's just once I have tossed it 6 times, I need 4 heads and 2 tails. We can visualize this with a tree diagram, right? And then we'll be grateful to have the formula. How about that? Because what's this look like? First, I make this thing nice and wide. Because if I toss a coin, I get either heads or tails. That's my first coin toss. My second coin toss, I have the same number of options, right? But it doesn't matter what happened before. I have heads, tails, head, tails. I might regret this. Right? This is the first coin toss. This is the second coin toss. We have to keep going for 6 tosses. Let's see if I can pull this off.
Oh, and this is 64.
1, 2, 1, 2, 1, 2, 2. Heads, tails, heads, tails. Okay, I think I can pull off one more. Oops. You could, at the end of all these, write out all the different permutations. But that's not what we care about, right? Or maybe okay, I surrender. Consider the tree diagram for how many flips did I manage? 1, 2, 3, 4 coin tosses. You could probably keep going if you were more meticulous than I to get 6 layers in there, but
That is dedication.
I give up. How many ways? Can we get 2 heads and 2 tails in 4 coin tosses? So we can use the tree, right? And just highlight all the options where we get exactly 2 heads and exactly 2 tails. So option number 1 is I start with heads, and I get another head. Then the next two have to be tails. If I flip and then after that, so if I already have two heads, then the rest are out, right? So then I move on. If I have heads and then tails, then one option is I could get my second heads, but then the last one would have to be tails. We're not done with that branch. If I get heads, tails, tails, I could finish with heads. And that's it for starting with heads. How about if I start with tails? I could get tails and then heads and then heads and then tails. Or I could get tails and then heads and then tails and then heads. Or I could get tails, tails, head, head. Or I could get nothing. This tells me that, right, all these different permutations that are highlighted, heads, heads, tails, tails, heads, tails, heads, tails, heads, tail, tail, heads. Oops, sorry, tails, head, head, tails, tail, head, tail, head, tail, tail, head, head. Those are all my different permutations, but there are, or those are the permutations with exactly two heads and two tails. But there are 1, 2, 3, 4, 5, 6 different ways. There are 6 ways to get 2 heads and 2 tails in 4 tosses. What if we went out on a limb and said, okay, well, out of 4 tosses, I need to choose 2 of those to be tails, let's say, right? It doesn't matter, just like the horizontal and the vertical roots, right? You could pick tails or you could pick heads because if it's tails, then it's not heads, and if it's not tails, then it's heads, right? So what if we did 4 choose 2, then I have 4 factorial over 4 minus 2 factorial, 2 factorial. So I get, I'll put it on this new page here. 4 choose 2 is 4 times 3 times 2 factorial divided by 2 factorial, 2 factorial. Those 2 are going to cancel, and I get 4 times 3 divided by 2, which, drum roll please, is 6. And so it is the choose function. And so now we can look at, well, I don't want to draw it out, right? And I certainly don't want to map it out. Imagine tossing a coin 20 times, right? Then you need to have 20 layers to your tree, and that's just terrible. And you'd have to map them all out, right? How about exactly 13 out of 20 were tails, right? That sounds like a mess. So we can use combinations. So we toss it 6 times, and how many ways can it fall? 4 heads and 2 tails. So toss a coin 6 times and get 4 heads and 2 tails. Which one are you going to choose? 6 choose 4 or 6 choose 2? Doesn't matter. In fact, they're going to be the same. So let's try it. 6 choose 4 is going to be 6 factorial divided by 6 minus 4 factorial times 4 factorial. Or 6 choose 2 is 6 factorial over 6 minus 2 factorial times 2 factorial. Notice how those are the same. Neat. Maybe it's not obvious yet. 6 factorial over 2 factorial, 4 factorial, or 6 factorial over 4 factorial, 2 factorial. Either way. 6 times 5 times 4 factorial divided by 2 factorial, 4 factorial, or 6 times 5 times 4 factorial divided by 4 factorial, 2 factorial. Things are shaping up in both situations. I get 15 and 15. These are the same. These are the same since if we force 4 heads in 6 tosses, right, the remainder must be 2. 2 must be tails. Yeah. And if we force 2 tails, the remainder, or the remaining 4, must be heads. Right? There's that symmetry. Okay. So, although I feel like you could handle it as a real question on the test next week, a whole week from now, but I already promised it would be a bonus. So that's pretty fun. I do want to look through the questions, right? A lot of these questions are similar to what we just did, right? And so I guess I don't need to look through the questions, but try to rephrase all these questions into, or talk you into them being a combinations problem, because they're in the combination section, but also be able to identify them. I guess you'll know because it's the bonus, which I'll have to label. You'll know. All right. That is where we end chapter 7. And we've got lots of time to do homework, but that feels good, I think.
It does.
All right. Any questions before I stop this recording? Up in the recording. Did I record? Oh, phew, I did.